This is module number 3 in my Introduction to Tensors for Non-Mathematicians course that I've posted here on YouTube. This video specifically discusses certain fundamental characteristics of algebraic objects like arrays, primal vectors, matrices, and tensors. As this course title suggests, these videos are aimed at scientists and engineers that have some background in linear algebra but want to learn more about tensors. This module discusses a couple things. It discusses the concept of an algebraic object as a generic representation of any matrix or tensor. We discuss how the rank of an algebraic object dictates its structure and potential applications. We discuss how to quantify and represent the size of an algebraic object with a certain rank n, as well as the specific notation for representing the rank and size of an algebraic object. And I do know that probably differs from some other resources that you've seen out there. I have written a text to accompany these lectures. A link to that text will be provided in the description below once it's publicly available. I'm still working on that. If you have questions or corrections, please place them in the comments. I'll try to address them as quickly as possible. And as always, please like and subscribe to see more engineering and general STEM educational videos. Let's discuss some characteristics of algebraic objects. So first, what is an algebraic object? We're going to use that term to represent really the most generic description of a set of structured numbers that ranges from scalars to arrays to vectors to matrices, linear maps, tensors, bilinear forms. The list goes on and on. Now, the object, an algebraic object, can represent two types of thing. They can be grouped into two buckets. We have values. So something like a vector can represent a physical value. We've already seen this, right? We know that a vector can represent a location in some, 3 whatever dimensional space. And then we have forms and maps, which can be, described as functional or relationship based in nature, right? They represent the relationships between vectors and or scalar values, with one example being a linear map or a bilinear form. And we've already seen this as well, right? We know that we can describe an array Y as the product of a matrix A and array X, where this is a functional mapping. So the term is useful because it allows us to discuss characteristics of all of these, and these characteristics that we're going to talk about, specifically rank and size, they do apply to scalars, arrays, vectors, matrices, on and on. All right. So in this PowerPoint, the term rank describes the total number of row and column indices required to identify an element of an algebraic object. So let's take an example like a matrix. Okay, so we have a matrix A, and let's say it's 2 by 2. So I'm gonna try to stick with my notation. I'm using italic here to represent the sub-elements. Okay. Now, why am I drawing 2 brackets here? Because I need to index an element, I need to identify its row as well as its column. So I'll draw 2 brackets for each one of these. And then I'll close my matrix, and the superscripts indicate the row, so 1, 1, 2, 2. And the subscripts indicate the column. And so we can call this element 2, 2. We can call this element 1, 2. Now, if you're not familiar with this notation, you'll have to take a look at the previous video. We talked about the difference between what we call contravariant and covariant indices. Now, this is rank 2 because it requires 2 indices to identify the location of an element, or we could say it requires 2 spatial directions to draw it as a whole. So we can visualize rank as a positive scalar, it has to be positive, that describes the number of spatial directions required to represent an algebraic object on paper. Let's take a look at some examples. Scalars are rank 0. They're sort of like a point in some sort of n-dimensional space. They don't extend in any direction. So a scalar is rank 0. Arrays and vectors are rank 1. They're sort of analogous to like a line, right? They only extend in one spatial direction. Matrices and linear maps are rank 2. You could think of them like a square or a rectangle, right? They extend in two spatial directions. And algebraic objects with a rank 3 or higher, for those we really don't have great terms. Sometimes we call them 3D matrices, but we will have some terms that we bring up later, but for now we're just going to call them higher rank algebraic objects. Now we can visualize these higher rank algebraic objects as a queue or a stack of matrices, and we'll talk about that in a second. Now we are aware that the term rank is also used in linear algebra to describe the number of linearly independent rows or columns within a matrix, and this is exemplified by the term full rank matrix. We are going to choose the definition that we just talked about on the previous slide, aka the number of indices required to index or to identify an element over the latter, because it's commonly accepted within the field of tensor analysis. I saw some references that employ the term valency to describe the contravariant and covariant ranks. I'm not familiar with that. It seemed to be an alternative term, but I'm gonna stay away from terms where I don't understand the full context of what that means. If you do, please throw something in the comments. Okay, so let's now move on to our second characteristic, which is size. So our size, the size of any algebraic object, is going to be represented by, first, this script R. Now, why the script R? The script R indicates that this is some collection of real scalar values. R, we could use S, but again, we're gonna assume that they're equivalent. All the scalar values are real. Then we'll have some superscripts and some subscripts. Now, the total number of the subscripts will define what we call the covariant rank, and the total number of superscripts are representative of its contravariant rank. And inside of each one of these brackets, we will have a size value, which tells us how wide or tall, or you could say long, how many elements exist along that given rank. Now we also will call this the first covariant rank. We'll call this the second covariant rank. We could call this the third covariant rank. And then this would be the first contravariant and second contravariant ranks. So we generally start from the left and move to the right, where everything along the top is contravariant and everything along the bottom is covariant. Everything along the top represents a vertical movement within the matrix, and everything on the bottom represents a horizontal. I know this description is not super formal, but I'm trying to take what can be a difficult concept to understand and boil it down, like I said in the first video, into more layman-like terms. Now let's go back to this example. So we have a row-oriented array, X. And so because it's row-oriented, we're defining individual columns, right? The column only has one value, but they are columns. And so we use subscripts. So we have x1 all the way to x sub n call, where n call is the number of elements, or the number of columns. Now, as I said up here, right, along the horizontal direction, if we count elements along the horizontal direction, they go as subscripts. So that's why we have n call here as a subscript. Now let's take a look at a column-oriented array. All right, and here we have, first off, all of the indices are represented as superscripts, and we go from x1 to xn row, where the number of rows, again, each row only has one element, but we could call them rows, is denoted by this variable. And so we use the script R as well as the superscript n row to describe its size. Now, if you wanted to, you could include a bracket 1 to indicate that there's only one row. Here you could include a bracketed subscript 1 that indicates there's only one column, but we really don't need these. All right, now let's take a look at a rank 2 object. So here we are going to have a superscript as well as a subscript bracketed value in addition to the R. We're still assuming that our object is composed of real scalar values. We already talked about how we index these things. And now, why is the n row up top? We can kind of see that from looking at our example over here. It has n rows. And why is n column as a subscript? Because it has n columns. It's a little bit difficult to say, but hopefully the idea is coming across. Now, before I move on to this slide, I wanted to talk about expanding a rank 2 object to a rank 3 object. So let's take a look here at an object we're calling X, and I am going to make it pretty large to leave myself lots of room. Okay, so I'm going to start off. I want to try to match what's on the next slide. So, okay, we'll do it this way. So we start off with, let's say, a 3 by 2 matrix. So we have, and I'm not going to index the elements. I'm just going to say X, 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 X. All right. So we have 3 rows, 2 columns, and the size of this would be 3, 2. Okay. We have only one contravariant rank, the first one, and we only have one covariant rank, the first one. Now, what happens if I were to put a 4 here? So I'm introducing a second covariant. Let me write that down. A second covariant rank. Now, what does that mean in actuality for what I have drawn below? What it means is that each one of my elements is going to become its own array. Now, why am I drawing them as horizontal or row-oriented arrays? Because I added a contravariant rank. If I added a covariant rank, which is not what I'm doing, then they would become column-oriented. And then now, each element has 4. And we would index them in a similar way. So let's take a look at one value. Let's say we wanted to index this guy right here. Okay, we would say that's X. I'm gonna write it up here. That would be X. Okay. What is its first? Well, what's its only contravariant index? There's only one contravariant index. There's only one description of row. And so it's on the first, second, third row. Then, what's its first covariant index? So the first covariant index refers to these groups. So we have the first group and the second group horizontally. This is in the first group. So that is a 1. And then within the element, within the embedded array, it is the 4th element. So we would index it in that way. Just as a quick example, let's try, I'm just going to pick one at random. Let's try this one right here. What would that be? So that is, and I have to write a little bit smaller, I don't have that much room. That is on the second row. It is in the second group, right? The second of the groups, horizontal groups. And it is the first element within its embedded array. Again, a little bit difficult to use formal terminology here, but I'm hoping this demonstration elaborates on what we're going to show in later slides, because I didn't want to jump straight from this to this. I feel like it can be confusing. Now, this is a more general description of a rank 3 algebraic object. it's grouped in a similar way where we have the blue arrow and the blue index indicating the number of rows. Then we have the green indicating the number of columns along the first covariant rank, and then the red indicating the number of columns along the second covariant rank, and we use a similar size. Now, the one thing I do want to talk about is the upside down A, which many of you may be familiar with from mathematical notation, indicates all. So how do we use that here? I'm going to use that to represent an entire group of values. Like, let's say I want to describe this whole group right here. How would I do that? I mean, again, this is our own personal notation, so I can't promise you'll see this in other, resources. But what I'm going to do is I'm going to call it X, okay? And technically it should be bold still because it's a collection of values. Now, the group that we're looking to index is on the third row. So it is the third element along the first contravariant rank. And it is in the second grouping of columns. So it is the second element of the first covariant rank. I know this terminology can be a little bit confusing. And now, as opposed to putting a specific value in this third bracket, where it would be a 1, a 2, a 3, a 4, I can use that to indicate we want all of these. Now, some books will simply just not use any index there, and they use that to represent all of them. Okay, I know the notation can be a little bit hairy here, but we're going to do our best to stay on track. Now, different visualizations. It's relatively easy to visualize an algebraic object like an array or a matrix with a rank less than 3 on a 2D surface, like a piece of paper. And that makes sense because, right, you can represent something with only one spatial direction as 2D. You can represent something with two spatial directions as 2D. However, it's more difficult to represent 3 spatial directions in 2D. Now, this visualization refers to how elements and sub-elements are grouped to represent their values along the various ranks. For a rank 3 plus, greater than 3 object, there can be many valid visualizations, right? And you can see here, I'm not going to go into detail of these groupings because this will become something where I think the language will get away from me. It'll be a little bit too difficult for me to put in formal terms. So what I recommend is for this and the next slide, you may need to take a look at it on your own and sort of understand, ask yourself the question, how does this variable represent all of these sub-elements here? How does this represent all of these? And you can see we're using the all symbol to collect groups of sub-elements. Now, we can represent this as an array of matrices. We can represent it as, right, this stacked set of matrices, or like a 3D cube type of thing. Now, I'm generally going to stay away from this type of representation for one reason, and that's because we want to keep a strong separation between covariant and contravariant ranks, and with the 3D, it can be difficult to keep them separate. With the 2D representation, something like this, with the embedded additional ranks, we know that the horizontal ones will be covariant and the vertical ones will be contravariant. If at some point I mix up the terms covariant and contravariant, please put something in the comments and I'll try to correct it. As you can imagine, it's pretty difficult sometimes to use those terms in succession and keep them straight. So my apologies. And so here we have some different visualizations. So in this one, we group by the first contra and covariant ranks. Here we group by the second contra and covariant ranks. And again, I really don't know how useful it's going to be for me to go and look at these one by one. I would consider this to be an example that you may have to review on your own. The next module asks a familiar question. What is a tensor? Unlike the first intro video, however, this next module answers the question in more formal terms. This is something we really couldn't do without the background we gained from modules number 2 and number 3. A link to that next lecture is available in the description below, or will be available very soon. I look forward to reading your questions and potentially corrections in the comment section.